So next we consider, last time we defined the various colorings, and we show that using the R-greedy coloring, we can show the upper bound on graphs with the degeneracy. So if G is given and we want to partition it into R-1 degenerate graph, then number of colors needed is at most its degeneracy plus 1 over R and taken the ceiling. And this generalized the proof of chromatic number being at most delta plus 1, the maximum degree plus 1. Next theorem we can consider is that we know that Brooks theorem tells us that the chromatic number is at most the maximum degree. In undergraduate graph theory, last semester we proved it for least coloring, and we didn't really prove for Brooks. We proved the stronger theorem, which tells that even the least coloring, this holds. Obviously I forgot that if G is not an odd cycle and complete graph, then this also holds for least chromatic number. But if we just want to prove this for chromatic number, the proof idea is roughly the following. If this is one connected, then you just prove for this smaller graph and smaller graph, and you color this graph first and color this graph first and permute the coloring so that the color coincides on here, so you can finish the coloring. And also if your graph is not R regular, say for some R, then you put the vertex with the degree less than R on the last, and you can assume that it has some good connectivity, and it's put on the last, and then you order the vertices so that every vertex has at least one later neighbor except the last one. Then, and you run the greedy coloring from the left to right. And every time you color, you know that at least one neighbors are not yet colored, so all the number of previous neighbors is at most delta minus 1. So you have to avoid at most delta minus 1 color so you can color it. And then at the last moment, because it has degree smaller than delta, so here R is actually delta, sorry. So this is smaller than delta, so there are at most delta minus 1 colors to avoid. So in this case we can do. And if this is R regular, then basically what you do is you put Vn here, and then if this is not complete graph, then you can actually ensure that it has at least 2 neighbors which are non-adjacent. And you somehow put these 2 at the beginning, and then later again you make sure that this property holds. Every vertex has a later neighbor, and then you run the greedy coloring, then these both have the same color, and then rest of them gets at most delta previous neighbor, because one of its neighbor is not colored. So you can actually run the greedy algorithm until the end, and at the end it has delta previous neighbor, and 2 of them have the same color, so at least 1 color available here. That was the basic idea of the proof of Brooks theorem. And then here, this ordering ordering where every vertex has a one later neighbor except the last one. Let's give some name to this ordering. And we say on ascending ordering of the vertices of G, say 2Bn, is on ordering where each vertex except Pn has a higher indexed neighbor. So for given graph, you can always, for given connected graph and a vertex P, then you can always find an ascending ordering to this vertex. How do you do it? You find just find one spanning tree. And then in this spanning tree, let's consider this B as a root. And every time you take one leaf, and then you write this as B1. And then now you have another, take arbitrary, you delete this one vertex from the tree, and then you take another vertex and put it as B2, and delete it, and another vertex into B3, and so on. So that make sure that you, every time you take a non-root vertex, non-root leaf, because there are at least two leaves in every tree, and then at least one of them is non-root. So you can keep doing it until there is only one root left, then you put it at the last. Then, because of this spanning tree, every vertex has its parent. If you consider this spanning tree as a, rooted spanning tree. Or, at the moment of taking this, we have this spanning tree, and this vertex has a neighbor. And then this neighbor must be coming after this vertex. So with this ordering, it's easy to actually check that every vertex has a, neighbor with a higher index. So you can actually show that every connected graph, you can find the ascending ordering. So we know that, what do we know? We know this holds. And then we just show that this is at most give me a moment. So, and we know that, this inequality holds. And we actually know that this, say R minus 1, we have, say, this inequality. Later we will prove this. And in this inequality, actually there are many graphs satisfying the equality. But if you take, say, this smaller one, this connectivity coloring, then there are not many graphs actually satisfying this equality, meaning that this is strictly smaller than this. And this, actually can be generalized to the following theorem, which is a generalization of Brooks theorem, which is theorem by Matula. Let G be a connected graph. and if G is R regular and say RH connected, or is a complete graph with degree divisible by R, or an odd cycle when R equal 1. If one of the cases hold, then we can actually show that the graph is C sub R minus 1 coloring, C sub R minus 1 chromatic number is same as its maximum degree plus 1 over R. And all other cases, the C sub R minus 1 chromatic number is at most the ceiling of delta of G over R. So we can forget this one. So this is actually a generalization of Brooks theorem. So for Brooks theorem, if you apply R equal 1, then G is one regular 1H connected graph is K2, or complete graph with any degree, or odd cycle. So it's actually saying that complete graph or odd cycle then delta plus 1, otherwise it's delta, at most delta. And when R equal 1, you know that this is same as chromatic number. So again, how do we prove it? We want to prove the idea, use this idea of Brooks theorem's proof. We show that there is, if cut vertex, then we cut it into two graphs and then we induct. And then if not R regular graph, we take an ascending ordering to a vertex with less degree. And if R regular, then we take a vertex whose neighbors are not adjacent, and then we put them at the beginning, and then we do the ascending order. For that, let's prove a lemma first. This lemma, vaguely provides this situation. We have to choose one vertex whose neighborhood is not, neighborhood contains two vertices which are not adjacent. And then if you actually think about it, then, a bit more conditions are needed, and which are captured by this lemma. So let G be a two connected R regular graph, and which is not complete. If S is between 2 and R, and strictly smaller than R, then there exists a vertex X in G, and on set of size S, which is capital S, which is a subset of neighborhood of X, which does not contain all the neighbors of X, such that G minus S is connected. So once we delete it, it doesn't disconnect. And S is not a clique, meaning that it contains two vertices which are non-adjacent. So this S will be the vertices that we put at the beginning in here. So let's prove this lemma. So how do we do it? We choose a vertex G in G to maximize the order of largest component Q of G minus neighbor of G. And let T be the vertices in the component Q. So what's the situation? We have G and it has neighbors. Once you delete these neighbors in the graph, then you get this component T, and then say last smaller one. So we choose this G so that this T is the largest. I mean, it could be that the G and neighbor and the rest of them are still connected and rest of them is T. It could be possible. I mean, and we let U be the intersection of, neighbor of G and T. So some vertices sends neighbor to T, and some vertices, does not send any neighbors to, any edges to T. So that's U. And let W be the everything but T. T and U. So this is W. Then what do we know? There are no edges between T and W because all the vertices in U is defined as the neighbors of T. So if there exist non-adjacent vertices in W and U. So here U and somewhere here W, and that's not adjacent. Then what happened? In G, if you take W, and because G is adjacent to all the vertices in U, so W is not G. In that case, if you take this, and then we delete all the neighbors from G, then it contains, so all the vertices in T are there, and then U is also there. And then U has a neighbor in T, and then T forms a connected one. So in here, we have a component which contains all T and U, which is bigger than T. And U has a neighbor in T. This contradicts the choice of G. So this shows that all vertices in W is adjacent to all vertices in U. So what's it look like? We have U, and then T, we have W, and then this is complete bipartite graph between U and W. So we consider a vertex B in U. Then what do we know? Again, let's draw it in better way. G, U, and other neighbors, say V. then this B sends one neighbors in T. And then we say that the graph is regular. And this G has these R neighbors, and then B sends one out. So it can have at most R minus 1 neighbors in this neighborhood of G. So, okay, it sends this one edge and one edge, so R minus 2 neighbors here. So that means as B has a neighbor in T, and degree of B and degree of G is both R, we know that this doesn't happen. So neighborhood, let's say, neighborhood of G cannot be inside of neighborhood of B. So each vertex in U has a non-neighbor in U, because this part is in W, and we already showed that these are complete bipartite graph. So every vertex here and every vertex are adjacent. But we just showed that the vertex here must have at least one non-adjacent vertex, non-neighbor in here. So it must be the non-neighbor in U. So every vertex has a non-neighbor in U. This implies that U has size at least 2. So let's consider two cases. If S has size at least 3, then we can just let X be G. X is the vertex that we want to find. And let S be consists of S neighbors of G, omitting some vertex of U, but including a non-adjacent pair in U. So we have G and U and here. And you have at least 3 vertices, and then these are non-adjacent. Then you take S vertices here. So S is at most R minus 1. So you miss one vertex here, and then you take S minus 2 vertices more here, and then these 2. And then, if there are more here, then you add. So you take S vertices, so that it contains 2 non-adjacent vertices in U, and then you miss one here. Did I not turn off the Wi-Fi? Sorry. Where was I? Okay. Then, what happened? S is not a clique. And what do we have to show? S is not a clique, and G minus S is connected. So we have to show that G minus S is connected. But we know, since every vertex of U minus X, so the remaining vertex here is adjacent to some vertex of T and all of W, so G minus S is connected. So we have T, and then here we have W, And we know that this one vertex is adjacent to one vertex in T, at least one vertex in T, and everything in W. And then T itself is connected. So entire graph we get is connected. So in this case, we are done. And let's consider case 2. So if U has size 2, then what do we know? We know that you have 2 vertex here, and this has T, this send at least one edge, one edge. They might send to the same vertex, but at least one edge, one edge. And this sends, we have W here, and then this is adjacent to all of them and all of them. Then we know that this is R regular, so size of W cannot be too large. Every vertex of W, U is adjacent to some vertex in T and every vertex in W. So it's adjacent to in every vertex in W. So W size at most R-1. Since U is 2, has size 2, and every vertex in W has degree R. So vertex in W has at most 2 neighbors here, and then at most other neighbors in W. So W minus 1 plus 2 neighbor is the, that's the maximum possible degree that it can get. But we know that it has degree R. So we know that this W induces a case of R-1. It has R-1 vertices, and every vertex must have, degree R-2 here, and then 2 more neighbors here. So what's the situation? We have W, and then this 2, and this 2, and this is case of R-1. And since, has the 2 neighbors, 2 vertices, U and V. Say these 2 vertices be U and V and T. In U has degree R. So each has exactly 1 neighbor in T. Since R is at least 3, that's one of the assumptions. And U has 2 vertices. And the vertices in T has degree R. We have that T has more than 1 vertex. If T has 1 vertex and then U, then this has degree 2, which is a contradiction. So T has more than 1 vertex. And also, G is 2 connected. So UV has different neighbors, distinct neighbors in T. So what do? We let this be Y. Let Y be the neighbor of V in T. And we let X be this vertex B. And let S be the vertices consist of Y and any S minus 1 vertices in W. Then what do we get? Now, this S is inside of neighbor of this V, and S is now the clique. Also, G is 2 connected. So G minus Y is connected. Without this Y, the graph is connected. And now we want to show that, we are showing that after deleting S, the graph is still connected. The vertices of S minus Y, so these vertices has the same neighborhood, same close neighborhood. Close neighborhood is neighborhood together with its own vertex. As it has the same close neighborhood as the vertices of W minus S. So all the vertices here have the same neighborhood as here. So once we delete it, then this is complete graph, and then here we have U and the rest. So this must be a connected one, because again G minus Y is connected. And then how does it look like? V, U, and this is how it will look like. And we know that our assumption is that this is connected. Then once you delete some of the vertices here, then these remaining vertices have the exactly same load as these vertices. So once we are finding passes between two vertices, instead, if ever we want to use these vertices, we can instead of use this. So the remaining vertex here, at least one vertex remain. So here, so we have these again connected. So also G minus S is connected. So this proves the lemma. So now we have this lemma. Now to get, with this lemma on our hand, we can start the proof of Matula's theorem. We do that in the next video.